Autonomous first-order differential equations. An autonomous first-order differential equations is in the form of dy by dx equals the function of the y, where y is the dependent variable and x is the independent variable. Since dy by dx is the slope, therefore the f of y is a slope function. For the autonomous differential equation, a critical point is a real number c such that f at c is 0. A critical point is also called an equilibrium point or a stationary point. As dy by dx is the slope, if dy by dx is greater than 0, the solution is increasing. If dy by dx is less than 0, the solution is decreasing. A phase portrait or a phase line of the first order autonomous differential equations is the vertical line with the critical point and the arrow indicating algebraic signs. The arrow going up means the slope is positive. The arrow going down means the slope is negative, that representing the solution either increasing or decreasing on the interval. The critical points are categorized by 3 different cases. The first one, asymptotically stable or attractor, where both arrowheads on either side of the dot or the critical point toward C, or we can say the limit of the solution y as x approaches infinity equals c. The second case, the critical point is unstable or called repeller, where both arrowheads on either side of the dot label C point away from the point C. A semi-stable, when a solution is attracted to C from one side and repelled from the other side. Let's look at the example. For the given autonomous first-order differential equations, we are going to find the critical points, draw a phase portrait, classify each critical point as asymptotically stable, unstable, or semi-stable, and then sketch the typical solution curves in the region by hand, determined by the graphs of the equilibrium solutions. For example A, dy by dx equals y squared minus y to the third. If we factor y squared out, we have 1 minus y, and then let it be 0 to find the critical point. Therefore, we have y equals 0 and y equals 1 as a critical point. That's part A, critical point. And part B, we're going to draw the phase portrait. The phase portrait is the vertical line, represent the sign of the critical point, represent the sign of the differential equations or the autonomous differential equations with the position of the critical point. For this case, critical points are y equals 0 and y equals 1. So we determine the sign of dy by dx in each interval. For x greater than the value 1, the dy by dx will be negative. So in this region, dy by dx will be negative or less than 0. So the arrow coming down. So this is coming down. Just draw the vertical line, no arrows to begin with. For the region y greater than 1, dy by dx less than 0. So use the arrow pointing down, represent decreasing solution. For the value of the y between 0 and 1, the slope or dy by dx will be positive. We use the arrow up to represent the increasing solution. And then the last interval, where y is less than 0. If y is less than 0, the slope will remain positive. We use the arrow up to represent the increasing solution. Then part C, we are going to identify each, each critical point as stable, unstable, or semi-stable. In this case, at y equals 1, we have the arrows coming toward to the point y equals 1. Therefore, y equals 1 is a stable critical point. A stable critical point called attractor. And at y equals 0, the upper part, the arrow going away, the lower part, the arrows coming toward to that point. Therefore, y equals 0 is a semi-stable point. And then in part D, we are going to sketch the solution curve by hand. The region for y greater than 1, the solution is decreasing. So decreasing toward to the line y equals 1. For y between 0 and 1, the solution curve is increasing toward to the line y equals 1. For the region of y less than 0, the solution curve is increasing toward to the line y equals 0.